Good evening, everyone. Welcome to TACO After Dark, or TAD. I had to abbreviate up here, commercial version. So my name is Brett Zerba, applications engineer for TACO. I will be moderating tonight's presentation like I did last week for some of you that joined us. Rich Medeiros will be doing the main presenting. And tonight's topic is expansion tanks. Everything you need to know about them. We'll even tell you why we put them in systems or why they should be put in HVAC hydronic systems. And before we get too far into tonight's presentation, if you could just bear with us. Hopefully you can see a screen right now, a big TACO After Dark, a couple of pictures there of a couple of ugly guys on the left and maybe a pretty young little girl on the right. If you can put up a hand wave there or a question mark, if you can wave your hands, I'd appreciate it. I haven't seen anyone wave their hands. That's not okay. Good. Daniel, Lombardo, Mike, thank you very much. I appreciate that. That's good. That's always a good sign. For you, let's see. We don't have any handouts tonight, but 24 hours from tonight, when this is over, hopefully after 9, like last week, you'll get an email with access to tonight's recording and your PDH hour certificate. If you need that, you can download that, and hopefully it's acceptable in the state that any PEs are registered in out there. Professional engineers, there are other meanings for PE, and maybe Rich can go over that, but nonetheless, welcome aboard. Just like last week, we want to be informative, and Rich, for any of you that sat in last week, his knowledge and expertise in this HVAC hydronics, HVAC in general, is second to none as far as I'm concerned. And if you sat in last week, hopefully you picked up a lot of stuff. But please, just like last week, ask questions. Type them in the chat, the question area. I'll be moderating them. The more questions, the merrier. And really, that helps tonight's presentation. And tonight's presentation is all about expansion tanks. You can see a picture of a TACO CBX, and Rich is going to tell you which expansion tank that is up in the top right-hand corner. And for you folks that are attending tonight that don't know, TACO is a privately held company led by Johnny White Jr., and he's third generation. And his fifth generation is shown in the bottom right, little Madison Marie White. And she is now 3 months old, almost 3 months old. We'll all know when that happens very shortly. And she's quite the little youngster. And a good friend of mine, John Barba, is got to meet her recently, and he told me that she was just a delight. Although when you're 3, you don't do much, but well, you all know what 3 months old do. Anyways, I digress. TACO is a family-held company, headquarters in Cranston, Rhode Island, but we're a worldwide company. And we want you to think commercial tonight, right? And hopefully some of you are on here to learn about some commercial aspects of TACO. And John, Rick, and Dave have done a great job with this TACO After Dark series, talking about the residential product, the wholesale product. The double O's, right? TACO and double O's is something that we're world known for. Our wet rotor circulators, which we continue to make on a daily basis, which is just phenomenal. I was at the facility today and watching them being assembled, talking to some of my friends out there in the factory that do a heck of a job for us, and they have done a heck of a job through this whole pandemic situation. But we also make commercial products, right? And last week we talked about the pumps, and Rich gave you a good introduction to the pump curves, but he showed you some of our products. And tonight we're going to talk about more of our welded product division, which is located, our headquarters are in Cranston, Rhode Island. For some of you that I recognize some names, know New England a little bit. We're kind of a small area in New England. If you look on the map, the United States map, our welded products division is located in Fall River, Mass, which is right over the border. I mean, it's like 20 minutes away. Not quite a stone's throw, but nonetheless, it's not very far away. And they make our welded products division, and I'm sure Rich will talk much more about some of their other capabilities there. But one of the products that they make on a daily basis is these expansion tanks, all different types, and Rich will get into it. And he'll get into how to size them as well. And then in a couple of weeks from tonight, we're taking next week off, July 4th week. Rich and I decided, I know I'm going to the beach. I'm not sure, Rich may not be going to the beach, but I'm sure he has some plans. So we won't be back together for 2 weeks from tonight. I believe that's the 14th. I can't believe tomorrow's July 1st. I cannot believe June is already gone and tomorrow's July 4th. Us here in New England have just gone through our second official heat wave of June, which is unheard of as far as I'm concerned. A couple of weeks ago, we had 5 straight days of 90+ degrees, and today was the 3rd straight day of 90+ degrees, and that defines a heat wave. These weather people, they got all kinds of different definitions, but nonetheless, these heat waves are hopefully coming to an end. Well, I know they are for June because today's the last day of June. So I'm kind of done yapping. I see a good friend, a new friend from Hawaii on the line, Mr. Gellert. Welcome, welcome. I see a Milwaukee Area Technical College. Thank you. We had some great questions from some universities or colleges, universities, community college last week, and hopefully we continue to get that. And really, education, right? That's what we're striving for. And hopefully TACO, I know internally TACO is known for education, and that's what we want to be known for externally as well. We really want to educate all of you. And then we have some reps out there, Chris and Neil from different folks out there. I know Mark from Canada is out there, and there's many more. I can't cover all the names that are out there. So I think I've covered all the groundworks, but please, I can't emphasize this enough. Ask questions. You know, expansion tanks and how to size them, they're so important in a system. They may be forgotten or overlooked sometimes, but the more we all can learn, and like I said last week, when you guys ask questions, when you folks ask questions, I learn on a daily basis, and us presenters learn on a daily basis. I can't emphasize that enough. And I have to give Rich the screen. I'm making Rich the presenter here, so I need to yap for a couple more seconds while he brings his screen up. John, you want to say hi to everybody and then turn it over to Rich?
Sure. Thank you. I'd say hi to everybody. Hi, everybody. This is John Barba from TACO, and I just wanted to welcome everybody here. Thank you so much for being with us. And again, I want to just reiterate what Brett said. On your control panel, way down at the bottom, there's that place to ask questions and chat. That's going to be how you're going to ask questions, and Brett will be monitoring those. So ask questions. That's what this is all about. And just to make sure everybody knows how to do that, if you could do us a quick favor, just go to that portion and just type in a hi, hello, how are you? Just so I know that all the people out there know how to do this. So that's good. All right, we got one. Daniel, Jonathan, very good. Excellent. Very that's perfect. You guys got this. You guys got this. So that's a lot of folks chiming in. So please make sure you ask questions and keep the boys on their toes. So I'm gonna sign off for now, and I'm just gonna sit and listen and learn like the rest of you guys. So go get them, Rich.
Rich,
thanks.
Rich, before you take it away, there's a question I can answer already. Mohammed asked the question: is if someone missed these webinars, is there any way we can get access to these recorded videos? Yes, the answer is yes. If you go to the TACO website, tacocomfort.com, and you search around under training and the TACO After Dark, all the TACO After Dark webinars are posted there. So you should be able to see them there. And for chance, if you if you can't find one or whatever, please let us know, and we will make sure you get access to it or correct it that it's available. So take it away, Rich. Sorry to interrupt.
Well, thanks, Brett and John, for that great introduction. As you can see from my screen, we have the little cocktail just to the right of TACO After Dark. So one of our team members, Dave Holdoff, put this nice graphics together, and we want to thank Dave. And part of the structure here is that there is no structure. The idea is it's TACO After Dark, at least for us on the East Coast. I know it's different time periods throughout the globe, but it's a chance to relax, learn something, participate, informal. Maybe you'll hear a joke once in a while. By the way, if the joke comes from me, it's always a bad joke. So a quick intro for myself. My name's Rich Medeiros. I'm a mechanical engineer here at TACO, senior systems engineer, and one of the members of the training team. I am a PE, professional engineer, registered in several states, and I specialize in the engineering and design of HVAC systems, and I spent the majority of my career on the consulting side of the industry, and I was fortunate enough to join the TACO team almost 9 years ago now, Brett. Can you believe that? It'll be
Oh
9
my God.
years
I
in
can't believe that.
November.
I can't
It's
believe
unbelievable.
that. Holy moly.
Holy moly, as they say. So we're going to get right into it. So hopefully my first screen, there it is. It says expansion tanks. And what are some of the things we're going to cover this evening? Well, we're going to talk about why do we need expansion tanks. We'll talk a little bit about the types of expansion tanks. We'll talk about Boyles Law. Boyles Law is the foundation of the operation of modern expansion tanks. We'll talk about expansion tank sizing, expansion tank selection, and then we'll talk about the impact of locating the expansion tank in different parts of the building. And then questions. However, we don't have to wait for questions at the end, as Brett and John were talking about a moment ago. Ask your questions at any time, and then Brett will be monitoring those questions, and he'll ask me to pause periodically, so we'll be sure to answer those questions. And then periodically, I will stop, and I'll ask Brett, do we have any questions out there? So that's the general format of how we're handling this evening.
Hey, Rich.
Yes.
We do have a statement/question that someone can't hear the audio. I have to believe everyone else can. So please, if you can't, you may have to log out, log back in, or check your connections. But if there's a mass people that can't hear the audio, I don't know. Audio okay, Douglas said. Thank you very much. So anyways, back to you, Rich.
So from where you're sitting, Brett, is the audio clear? Does it sound good?
You sound awesome. It's like
Sounds
you're
awesome.
right. It sounds like you're, I'm on the North Shore of Mass. You're on the South Shore of Mass. Well, we're 60 miles apart. Sounds like we're 60 miles apart or closer.
Yeah, it sounds like we're in the same room, doesn't it?
There you go.
Technology is amazing. So let's get right into it. So why do we need expansion tanks? Well, I have a little diagram here of a very, very simplified system. And this is known as a closed loop system. If you look at the piping system we have on this little diagram, we've got a boiler for making hot water. We have a primary, I'm going to point to it here. We have a primary circulating pump. We have a hydraulic separator. This actually is a product that TACO manufactures. We call it our 5900 hydraulic separator. So this on the left side is traditionally known as the primary loop. And then on the right side of the heat exchanger, which the piping, by the way, kind of wraps around, I'll kind of trace it out here. So here's where the piping is. It goes all the way around and down along the bottom here. This is all part of the secondary piping system. Come all the way back. It's kind of a torturous path, but hopefully you get the idea that this is the place that we do the piping, racing. Okay. So, and it's the reason we call it a closed loop system is because it's closed to the atmosphere. The water is contained in the pipe. Nothing is exposed to the atmosphere, which means that when the water heats up as a function of the boiler running, and in this case, the boiler has the capability of heating that water up to 180 degrees, that water will expand. And when it expands, it has to have some place to go, so it goes inside the expansion tank. I'm going to talk a lot about the expansion tank this evening. So why do we need expansion tanks? Very simply, we have a closed loop pressurized system that when we add heat to the system, that fluid, in this case water for this evening's discussion, is going to expand as a function of being heated up. And when it expands, we need to have a place for that to go, and we have a device called an expansion tank. And the expansion tank allows the the fluid to expand without any negative effects on the system. So that's why we need expansion tanks, because every closed loop system will expand with an increase in temperature. The fluid, in this case water, will expand and it has to have some place to go. Here's a quick side note. I actually got a call from one of the facilities managers at Taco Cranston. Did you say you were in Cranston today, Brett?
Yes, I was.
So I don't know if you ran across Mike Sorelli, but Mike called me and they were having a problem, and we're actually going to talk about this today. And the first thing I said to him was, do we have any pressure shown at the expansion tank? And it turns out we did not. So they had a leak somewhere in the system and the water leaked out and we lost the pressure, and then they had a problem pumping the water around the system. So yeah, we had a real live problem to solve today with respect to expansion tanks. So expansion tanks are extremely
Hey,
important.
Rich, would you recommend that this diagram not be used for design purposes? Someone's asking, where's the makeup water?
Yeah,
where is
this is
makeup?
really a very simplified diagram. I purposely took some things out not to make it more complex than what it has to be, but I could diagrammatically indicate the makeup water. So I might have a makeup water station over here. I'm kind of drawing a little rectangle, and I could just I could label it makeup water. I'm gonna put just an MW for makeup water. And that makeup water would connect ultimately, usually it connects right here to the expansion tank line. And that makeup water is coming from some kind of source. And usually it's the city. So usually it comes from municipal water supply, but you might have a facility where the water supply comes from a well. So the makeup water comes into the building and connects to the line usually that's goes out the expansion tank. And I purposely left that off because I didn't want to make it too confusing for everyone. Excuse me, 1 second. Sorry about that. I've got a bottle of water here to help me with my voice this evening. So yes, and that makeup water device usually has a pressure regulator in it, and we use it to regulate the water pressure. And we're actually going to see this in a little bit more detail in a few minutes. So hopefully that answered that quick question, Brett.
Yeah, and there's another one which is great pertaining to this drawing. Does the boiler primary loop need an expansion tank?
Well, in this case, we're using a hydraulic separator. Let me point to that. So the hydraulic separator actually acts as a bridge between the primary and the secondary loop. And so if you can kind of think of yourself as a molecule-sized human being floating on a molecule-size raft, you actually can float between the primary piping system and the secondary. They're all open to each other through this hydraulic separator. There's the primary piping and there's the secondary piping. And because these are all interconnected, we do not need to have an expansion tank on the boiler side, which is the primary side. So we only need one expansion tank for this system. And as Brett was saying earlier, we use this for training purposes, so don't use this diagram for your design. This is just intended for training purposes. We leave a lot of things out so that we can kind of just focus in on the individual component that we're thinking about this evening. Okay.
Excellent.
These are great questions, Brett.
Yep.
You're getting them early in the evening here, which is also a good thing, as they say. All right, so we'll erase those lines. So let's go talk a little bit about, well, first we have to get the slides to advance, right? Okay, so let's talk a little bit about the types of expansion tanks that we have access to. And by the way, the expansion tank types, they're somewhat generic in the industry. We at TACO have specific model numbers for different types of expansion tanks, but almost all expansion tanks that are used in the industry today fall into one of these categories. So I'm just going to list them by word, but don't worry about copying the words down. Again, Brett, as mentioned earlier, you can have access to this recording, but we will show you photographs in a minute and go over them in some detail. So, but I do like to list them first. So the types of expansion tanks that we typically see in our industry today include plain steel tanks. That's the first major category. A second category is called bladder style tanks, and they have two subcategories. And the first one is called a full acceptance, and I'll get into the definition of each one of these in a minute. And then we also have partial acceptance. And then the last category is called a diaphragm style expansion tank, and they are typically known as partial acceptance tanks. So that's it, 3 major categories, and under the bladder style tanks, 2 subcategories. So we can kind of think of 4 different styles of expansion tanks. So we have some photographs to share with everyone. So the first one is a plain steel tank, and as the name implies, this is nothing more than a steel container. This one happens to be mounted horizontally. I can grab my little pen here. And it has 2 connections. One connection, let's say a pipe is connected to the bottom over here, and that typically goes to an isolation valve, and then that allows us to open that valve if we need to blow down the tank, and that would go to a floor drain. So I'll just label that floor drain over here. There's the floor drain. And that's a nice floor drain, Brett, don't you think?
It is. Good picture.
Nice picture. And then the other connection at the bottom, that goes to the system piping. So I'll just kind of use a little kind of what looks sort of like an acid break in the pipe, and I'll just say that that goes to the system. So those are the 2 connections at the bottom of the plain steel tank. I'm a little slow in my lettering today, Brett, but I think most people get the idea. So there's the system. And then over here on the left-hand side, we have 2 connections, and that's where you would put a sight glass, a special glass tube that allows us to see the water level in the glass tube, which is the same as the water level inside the tank. And because this is a plain steel tank, at the bottom is where the water is, so I'll put a big W for water, and at the top is where the air is. So one of the disadvantages of a plain steel tank is that since the water is in contact with the air, then the air sometimes over time will actually go into the water as solution. And when that happens, the water level inside the tank begins to rise. And that's why you need a sight glass over here, so you can keep track of the water level. So if the water goes way up here, then the water level in the sight glass would also be up there. I'll kind of make a squiggly line here. And that tells the operator it's time to open this blowdown valve here and drain some of the water out of the tank. Because if you don't, eventually the tank will become waterlogged, and there'll be no place for the water to go, and then that'll probably set off the pressure relief valve, and that's not a good thing. So that's it. Plain steel tanks are very, very simple. We actually don't see too many plain steel tanks being used in a modern hydronic system design today. There are a couple of folks still out there using them, but for the overwhelming majority of systems are used a bladder style tank, which we'll get to in a minute. And so the plain steel tank is really more for the replacement market. There are plenty of older buildings that were designed and built around plain steel tanks, and we manufacture them, and most of the ones that we manufacture go to the replacement market. So that's an existing plain steel tank. Someone wants to replace it with a new one. They tell us what the dimensions are and what the pressure rating is, and we can build a new tank for them. So any questions about plain steel tanks?
Actually, we do have a good question about plain steel tanks from Chris. How does air get back in the tank once mixed with water? Ooh.
That's a great question.
Yeah.
Yeah.
It gets ugly.
It gets ugly. Yeah, so on the piping system, there will be devices that will allow the air to enter the tank and ultimately displace some of the water in the tank. But over time, what happens is that the air gets compressed as the water level increases, goes up the tank, the air gets compressed and the pressure inside the tank increases. So when we open the blowdown valve, the natural expansion, because the water is under pressure, forces the water out and the air expands a little bit. So that's how the air gets back into the tank. So there are devices in the piping system that allow the air to enter the tank. And then also if you're blowing down, the air will expand and displace some of the water. Good questions.
Yeah, that was a good question.
Okay. So now let's talk about the next category. And the next category is called a bladder style tank. And we're initially going to talk about a full acceptance. So now we're going to talk about what this means. Let's talk about the, well, let's look at the cutaway photograph over here. So this is called a bladder style tank. It has a steel container. It's obviously the steel has been cut away for demonstration purposes. And inside that steel container is a rubber bladder that looks a little bit like a balloon. And if I made a very simple diagram up here, there's the steel container and the balloon is connected to the piping system. Kind of think an imaginary balloon here, but it's actually called a bladder. And then the piping system is connected to the top. So the water enters the bladder, that's inside the bladder. And then between the bladder and the steel container, that's the air space. I'll put a little A there for air. And the top is where we connect to the piping system. So there's a connection to the piping system. All right. Now, what you cannot see from this angle is that there is protected by this little round cover here, kind of like a cylinder. Inside there is a Schrader valve, and here's a picture of a Schrader valve. And this is the Schrader valve that's used inside an expansion tank to add air. And the Schrader valve was invented by a gentleman by the name of August Schrader, and he invented the Schrader valve in 1891. 1891. So the Schrader valve is the same valve, by the way, that's used on your car tires, a variation of it. It's used on your bicycle tires. It's used in expansion tanks for charging the air. And it's been around since 1891. So hopefully the guy had a patent on. I know he had a patent in 1891, and I hope he kept it because he'd be a rich person today. I don't know if he's still alive. I have a feeling he's not, but you never know.
He actually invented it in August of 1891.
Did he invent it in August?
I don't know. It sounds good.
Sounds good.
I had a 1 out of 12 chance, so
One-
I rolled the dice.
Okay, so the full acceptance term means that the bladder itself has the same physical volume, or it holds the same amount of volume as the steel container. So if the steel container, I'm just making up a number here, is 200 gallons, let's assume that our steel container is 200 gallons, then that means that the bladder can hold 200 gallons. It can accept an expansion volume of 200 gallons. So when the balloon or bladder has the same volume as the steel container, we say that that's a full acceptance tank. And so that's where the definition comes from. So the full definition or name, this is called a bladder style full acceptance tank. And in the jargon of TACO, that's called a CA expansion tank. So any questions about what we have so far?
No, I got some questions, and we will answer them, but I'm going to hold back right now for now.
Okay. So now we've talked about the second category. So let's go to the third category. And the third category is again a bladder style tank, only in this case, it's called a partial acceptance, And if we look at the photograph on the right, again, we see the cutaway. Here's the steel container. And here is the bladder. And as you can see, the bladder is dramatically smaller than the one in the previous photograph. And that is a partial acceptance, which means that the bladder volume is now a percentage of the steel volume. So using our reference number before of 200 gallons, if I just say that the steel container is 200 gallons, now, I don't know the exact volume of this particular tank in front of us, but I'm just make up a number. Let's assume that the bladder can only hold 50 gallons of water, 50, so put a 50 over here. And since the bladder volume is less than the tank volume, that's called a partial acceptance. So whenever you see the term partial acceptance, that means that the bladder only holds a portion of the volume that the steel container has. And again, like before, you can see there is the collar that protects the Schrader valve because the air is added to the top. So this would be the air right here. That's where the compressed air goes. And inside the bladder is where the water goes. And although you can't see it in this photograph, the pipe is actually connected to the bottom of this guy. And the water enters the tank from the bottom. So it would be, if I kind of drew a little dotted line here indicating that it's inside there, it would connect to the bottom of that bladder. So that's called a bladder style partial acceptance. And again, in the world of TACO, that's called a CBX tank, CBX. Any questions about that one?
Yeah, the typical question we get when we start talking CBXs and CAs and what are the benefits of using a partial acceptance tank versus full acceptance?
Well, that actually leads us into a great thing. So let's go back to the full acceptance. One of the things that this particular tank has is that it's not really, you can't see it in the photograph, but there is a connection at the top. And this top connection, you can see these bolts around here. It's like a flange connection. See all those little bolts? They can be removed and this flange can come off and the tank bladder, the bladder can actually be removed off the top of the tank. So you can replace the bladder in this style tank. Now we do have the other style that I just showed you a moment ago. You can also change, oops, let's go back here. Yep, you can also change the bladder in this style tank. However, the bladder is physically smaller than in the previous tank because it's only partial acceptance. So this tank is a little bit less expensive. It has a smaller bladder, so it's a little bit less expensive. So if you're trying to make a decision between the full acceptance and the partial acceptance, a lot of people will select the partial acceptance because it's a little bit less expensive than the full acceptance. But I will say that in our example, we said the tank was, the steel container was 200 gallons, and the bladder, we just assumed, for example, that it could hold 50 gallons. Well, if you try to put more than 50 gallons into the bladder, you run the risk of rupturing the bladder. So one of the advantages of a full acceptance tank is that the bladder will hold the same volume as the steel container, which means you can't rupture the tank by filling up the bladder with water 100%. If you try filling the bladder of a partial acceptance tank greater than its acceptance volume, and in our example, we said that acceptance volume was 50 gallons. Let's say you tried to put 70 gallons in there. You run the risk of rupturing the bladder because it cannot hold more than 50 gallons. It will hold a little bit more than 50 gallons, but not dramatically more. And certainly if you get up around 70 or 80 gallons, you run the risk of rupturing the bladder. So why choose the full acceptance over the partial acceptance or vice versa? Well, you might select the full over the partial because the full was kind of idiot proof. If for some reason the air should leak out and the bladder fills up with water, it will just fill up to the full volume of the steel container. And so it can't hurt the bladder. In this example, where you have partial acceptance and the bladder can only hold 50 gallons. If you try to put more than 50 gallons in there, you stretch the rubber material and it will eventually fail. And then it would not be as foolproof as the other one. However, it costs less money and the bladder is smaller and means it not only costs less, but it's less expensive to replace. So it's a money issue. Any other questions about that?
A lot of things are money issues in life, isn't it?
Yeah, I know it.
So someone has a great question. So, well, so we have you have in the old days, we had plain steel tanks, and then we converted to bladder, some type of bladder steel, bladder style tank,
Yes.
full or partial or whatever. Why did the industry do that?
Well, one of the reasons is that you can pre-charge. In other words, you can add compressed air. Let me put a big letter A here. You can add compressed air to this void space between the bladder and the steel container. So I'll put an A in there for air. And whenever you can pre-charge the tank, then you can reduce the physical size of the tank. So they're smaller, they're more compact. And the second reason is that the water, as I said earlier, is connected to a pipe that's in the bottom here, and I kind of made a dotted line. That goes up inside the bladder. So the water that's inside the bladder does not mix with the air. So you never have to worry about the tank becoming waterlogged because the air is being dissolved into the water. Can't do that because it's separated by the bladder unless the bladder fails. Then if the bladder fails, then the tank will fill up with water, the air will be displaced by the water, or the air will go into solution and the tank will become waterlogged. So that's not a good thing. So we're talking about normal operation. Under normal operation, the water is physically separated by the rubber membrane in the bladder from the air, and so it doesn't go into solution. So it makes it much easier to control the air that's in your system. Air is not a good thing in a pipe hydronic system. And then as the second thing, as I said, it also allows for a physically smaller tank because you can pre-charge or pressurize the tank before you connect it to the system. So those are the two major reasons.
Great. I mean, keeping the air and water separate and the size of the tank. I mean, that's the simple answer.
Yeah, that's yeah. That's like keeping, well, no, I won't go down that.
Onward and upward.
Onward and upward, as they say. Okay, so now let's go to the last category. And the last category is called a diaphragm style tank. And the diaphragm style tank, again, we're looking at the steel container. You can see these have there's lots of things that are common. There is the collar at the top that holds the Schrader valve. There's the air side of the tank. And there's the water comes into the bottom. So there's the water. You can actually see the connection on the left here for the piping connection on the bottom. And in this case, it looks like a rubber bowl, and we call it a diaphragm. It's not a balloon shaped anymore. It's like a bowl, and it's connected to the inside circumference of the steel container. And again, this is a partial acceptance. It'll only hold a percentage of the water compared to the full volume of the container itself. So again, using our numbers from before, perhaps the steel container is 200 gallons, but the water side can only hold perhaps, I'm going to make up a number here. Let's say the water can only hold, say 100 gallons, 100 gallons. And since the bladder has less volume than the steel container, again, that's called a partial acceptance. Now, one of the major sort of benefits to a diaphragm style tank is that they're very inexpensive. But the downside is that the bladder or diaphragm cannot be replaced. It cannot be serviced. If it should fail for any reason, you have to dispose of the tank. We cannot rebuild the tank and put a new diaphragm inside. So the downside is that it cannot be serviced, but the upside is that it's relatively inexpensive. And when you're talking about relatively small systems, the diaphragm style tanks are very, very economical. And because most people put in smaller systems, they can be they can easily be replaced. You can take them out, put a new one in. If you have the new one, it could probably take less than a half a day to change out the tank. So that's called a diaphragm style tank. It's a partial acceptance. There are no full acceptance diaphragm style tanks. They are relatively inexpensive, but they cannot be repaired. If the diaphragm should fail for some reason, it has to be disposed of, and you have to buy a new one. So those are the major categories of expansion tanks. And again, in the TACO world, that's called a CX style tank. Okay. Any other questions before I move on, Brett?
Nope, keep moving.
All right, so now let's talk a little bit about the science of expansion tanks. So we have to talk a little bit about Boyles Law. So Boyles Law was invented by a guy named Robert Boyle in 1662. And Boyle's law states that the pressure of an ideal gas is indirectly proportional to its volume at constant temperature. And the formula that we use in the industry is as follows. It says that P1 times V1 equals P2 times V2. And I'm going to explain this in detail in a moment. And in this case, the volume can be any volumetric measurement. It could be gallons or cubic feet or cubic meters. And for tonight's discussion, we're going to talk about it in gallons, but the pressure always has to be in absolute. So we're going to use the term pounds per square inch absolute. So whenever we're talking about Boyle's law and his formula, which he published in 1662, we're talking about the relationship of two containers where we're talking about the pressure and the volume, and I'll show you an example of this in a minute. The volume in our discussion this evening will be in gallons, and the pressure will be in pounds per square inch absolute. Pounds per square inch absolute. Okay, so let's go through what that actually means. So I have two containers. I have glass containers, so we can kind of pretend that we can see inside. And we're going to assume for a moment, I put a note down here, do not do this at home. This is not something we want you to do, but this will kind of demonstrate what's going on here. So let's look at these two containers as they pertain to Boyle's law. So I have a container, and let's assume that this container has air in it, and that volume of that container is 200 gallons, 200 gallons. There we go, GAL. And let's assume that I can put a pressure gauge over here. I'll put a pressure gauge, and we'll also say this is air. And when we talk about air in this case, we assume that it has similar properties, virtually identical to an ideal gas. So there's air. This container is full of air, and the volume of that container is 200 gallons. If we put a pressure gauge on here, let's just assume for a moment that the pressure gauge is reading 40 pounds per square inch gauge, PSIG. Now, assuming that I'm at atmospheric pressure, I'm at sea level, does anybody know, can they type in and tell me what the absolute pressure is on this, inside this container? If the gauge pressure is 40 pounds per square inch, I'm at sea level. I'll write that up here. Let's keep track of that. If I'm at sea level, can they, anybody type in and tell me what the absolute pressure would be?
We have some 55 PSI or 54.7 for 54.7.
54.7, yes, that's absolutely correct. The way we get that is we say that one atmosphere, ATM, in the units of pounds per square inch, one atmosphere at sea level has a sea level pressure of 14.7, someone just said it, PSIA. And to convert gauge pressure into absolute pressure, I have to add that 14.7. One atmosphere is equal to 14.7. So someone did say that correctly. So 40 plus, I'll put a little arrow over here, put a plus sign, 40 plus 14.7 is 54.7.
We had someone round it off, so I want to give him credit too. He went to 55, so that's not too bad.
You can use 55 for, I'm going to use this number for tonight's discussion. So 55 PSIA. Okay, so we have the pressure in this container is 54.7 psia, and the volume we just said was 200 gallons. That's the air volume. Okay, let's pretend that I connect a pipe to the bottom of this container on the right side here, and I let water go into this tank. And let's assume that I let water go in and I fill it up halfway. So this is water. I'll put a W for water, and let's say that the water is equal to 100 gallons. 100 gallons. Yeah, there it is, 100 gallons. And now the volume of the air, well, the volume of a whole container was 200 gallons, but the air volume has been compressed, and it's no longer 200 gallons like it was in the left tank. It's now 100 gallons. So the pressure on the air, because pressure volume relationship has to do with an ideal gas. It's not the water, it's the air. So the air volume is now 100 gallons, 100 gallons. And so we know that the volume, that V2 is now 100 gallons. So let's put that over here. V2 is equal to 100, and V1 is equal to 200. That makes sense to everybody? And since we said that the pressure is inversely proportional to the volume, so then if we want to figure out what P2 is, we would say that P2, and remember these pressure readings have to be absolute pressure. P2 is equal to P1, if we just rewrite that equation, times V1 divided by V2. And let's just fill in the numbers. I'll do my best to fill in the numbers, so I'm writing with the mouse here. 54.7. I won't put the units in. And it'll be V1, which is 200 gallons, divided by 100 gallons. And I'll put that in parentheses, so you'll see that you're multiplying these two numbers together. So essentially 200 divided by 100 is 2, and so the final pressure, P2, is going to be equal to 2 times 54.7. 2 times 54.7. Anybody know what that number is? Is anybody going to type that in? I'm trying to do simple arithmetic tonight, so we don't get hung up on the math.
Nothing yet.
Nobody,
109.4.
There you go.
We got three 109.4s.
109.4. And remember, we said that pressure is in pounds per square inch absolute, PSI.
Oh, a couple of people put that in, PSIA.
Yes,
in their
so
answer.
I'll put in PSIA. All right. So let's assume for a moment that I put a pressure gauge here, and I'm measuring gauge pressure. Well, to find gauge pressure, I know what the absolute pressure is, 109.4. Does anybody want to tell me what the gauge pressure is and how I got to that?
I'm watching.
I'm doing the arithmetic out here on my calculator.
80, Mario. Bunch of 80 and a 94.7 PSIG.
So the new pressure for gauge pressure should be 94.7. 94.7. And again, that's PSIG. So one of the things that we have to be careful of, PSIG, I should have put that PSIG to the right. Should I rewrite now? I think most people.
That's all right.
We'll be fine. So one of the mistakes we see all the time is we'll say, well, you've got a container, it's got 200 gallons, the original pressure is 40 PSIG. You allow 100 gallons of water to go in, the air gets compressed, it's a 2-to-1 ratio. What's the final pressure? A lot of people come back, they forget to convert into pounds per square inch absolute before they multiply it by the ratio of the volumes. and they come up when they say, well, it's 80 PSIG. And I said, no, you have to do the calculation by adding the atmospheric pressure. In this case is 14.7, which gives you 54.7 times 2, which is 109.4. That's the new pressure. Now you have to subtract 14.7 to find out what the gauge pressure is, and that's 94.7. So it's not 80, it's 94.7. So is everybody sort of tuned into what Boyles Law is and the fact that if we allow water to enter the container, that we will compress the air? Any questions about that?
Nope.
Okay. This is a major step forward. We've just
Boyles
demonstrated
Law at
Law.
close to 8 p.m. at night. Awesome.
I know it. Unbelievable. Okay. So what is my next slide here? Expansion tank sizing. So when it comes to an expansion tank, we need to know things like the minimum or fill pressure, which in our example before was what the pressure was at the beginning when the tank was empty. We need to know what the maximum pressure is, and we'll tell you how to figure out the minimum and maximum pressure in a system. We also need to know what the minimum temperature is for the fluid in our system. We need to know the maximum temperature, and we need to know the fluid type. That's very important. And the system volume, how many gallons of fluid, in our case tonight, we're still talking water, is there in the system. So if we know all of those things, we can figure out how big the expansion tank needs to be. So let's see how we can figure out what these different values need to be. So the first one we're going to figure out is the minimum or fill pressure. So I have a little diagram here, but first I'm going to say, before I show you the diagram, we are given the following information. We have a 75-foot tall simple office building, and we want to find the expansion tank size. So here's a little diagram of our 75-foot tall simple office building. Our mechanical room is down here on the first floor at the lowest level. And in that mechanical room is where we're going to have our expansion tank. So we'll just quickly look at what that looks like here. So here's our mechanical room on the lowest part of the building. We're going to assume this piping is all at the same elevation to kind of simplify things. And we'll assume that it's relatively close to the floor. We know in the real world it's not exactly on the floor, but we're going to pretend that it is. Okay, so let's look at the piping inside the building. I have piping that leaves my mechanical room. Let me grab my pen. Leaves my mechanical room and then runs from the lowest part of the building all the way up to the top of the building. Let's go like this. And I'm going to put in a little valve that I can open and close, put a little handle on this valve. And I'm going to have the discharge of that valve go to a plastic bucket, nice little plastic bucket. And this little plastic bucket, I got at Lowe's. That's one of my favorite stores is Lowe's, so that's going to be a blue bucket. Sometimes I go to Home Depot and the bucket is orange, but we're going to assume that the bucket is blue because it's I got it at Lowe's. So I'm going to allow, let's say I put another valve down here, and I'm going to open this valve down here and fill my piping system with water. Fill it up until it gets all the way to the top, and I just get a couple of drops of water coming out of my bucket. Then I close this valve. This valve is now closed. I just opened it to fill the piping system. And again, let's assume that the vertical pipe is 75 feet, goes from the highest point of the building to the lowest point in the building. If I put a pressure gauge right here, zingo, there's a pressure gauge, and I'm measuring the pressure, I fill the piping system with water and I measure that pressure. Can anybody guess what the pressure is in pounds per square inch gauge? I'm going to write the PSIG up here, PSIG. What is the pressure at the bottom based on the example that I just showed you?
We got a lot of
I closed this valve too. I'm going to close that valve so no more water leaks out.
We have some 32.6 PSIG, 32.55 PSIG, 32.5 PSI, 32.5 PSIG, 32. I think I covered the gamut there.
Yes, the pressure is going to be approximately equal to 32.5, I'll put a decimal point here, 5 PSIG. That's what the pressure is going to read on my pressure gauge at the bottom. And the way I figured that out was I simply took the height of the building, 75 feet, which is the height of my piping system, and I divided that by 2.31. And the reason I did that is because if I have a column of water, there's a column of water. And let's assume that my column of water, this is not to scale relative to the building. This is just a column of water. Let's say the water is filled up in this tube. And the height of that column of water is 2.31 feet, 2.31. So can I squeeze that over here? Yes, I can. 2.31. If I make that 2.31 feet, and if I put a pressure gauge at the very, very bottom right here, my pressure gauge is going to read 1 pound per square inch, 1 PSIG, 1 PSIG. Oh, I can barely fit the G in. Oh my God. So the relationship between the height of the fluid and the pressure is you need every 2.31 feet, you come up with 1 PSIG. So my building is 75 feet, and I simply took 75 divided by 2.31, and magically I came up, I rounded it off to 32.5 PSIG. And someone typed that in, and they had the right answer.
Oh yeah, but to be quite honest, in reality, when I look at that pressure gauge, it's going to say 35 because the pressure gauge is not going to be reading 32.5. I won't be able to see it. I'm sorry. Unless you really got a fancy pressure gauge.
Well, we're going to assume for a moment that our pressure gauges have been calibrated and they're extremely accurate, and they're 24 inches in diameter, so they're easy to read. No, nobody makes gauges that big.
I'm up to it. My magnifiers are up to 2.75.
If I put a pressure gauge at the top,
oh boy, here's the
here's where it gets tough. What will that pressure gauge at the top of this piping system read? And again, I'm looking for pounds per square inch PSIG. What will the pressure gauge in this little example? What's the pressure at the top of the building? What's that going to read? Anybody want to take a guess at that one?
Christopher and Dennis and Ronoli, they're saying 0.
That's correct. Awesome. Everybody's on the ball tonight. Whoa!
I know we got a good crowd, and Wayne's answered every question correctly.
Should we give Wayne? We can next time we see Wayne, we'll bring him over to Subway, and we'll get him a half a sandwich with no drinks and no chips, just a half a sandwich.
We should invite him. We should invite him to Taco Tuesday. Taco Tuesday. That's right.
So yes, the pressure gauge at the top of this system will read PSIG. Now, in a hydronic system, I don't want 0 pounds at the top. I want something different than that. Anybody want to take a guess as to what the pressure I want at the top? While you're doing that, I'm going to write a little thing over here on the left.
We've got answers from 5 to 4 to 7.5. So, or 15.
Most engineers will say that they want somewhere between 5 and 10 pounds per square inch gauge at the top of the building. And for today's discussion, to make the arithmetic simple, I'm going to go halfway between those two and say I would like to have 7.5 pounds PSIG at the top of my piping system. If the pressure at the top of my piping system is 7.5 PSIG, the reason I want pressure at the top of the system for multiple reasons. First of all, I want to have enough pressure to push the air out. So if I have some air vents at the top, and if there's any air trapped at the top of the piping system, I want to have enough pressure to push the air out. I want to have enough pressure to prevent cavitation, either through a pump or some other device connected to the system. And I want to have enough pressure so I don't have my piping system is not airbound in any way. If I have 7.5 at the top, what is my pounds per square inch at the bottom where I have my gauge down here. If I've increased the pressure until I get 7.5 at the top, what's my new pressure at the bottom?
Oh,
Anybody want-
Mario jumped in quickly today. He said 40, so didn't Chris.
40 is correct. So you guys get it. 40 PSIG. And how did I
All
come
right,
up
so
with that? I simply took what pressure I wanted, which was 7.5 at the top, and I added that to the pressure that's already at the bottom, 32.5 plus 7.5 is 40 PSIG. That's why I picked 7.5. I wanted it to come out simple, easy math. So that's my minimum pressure that I want at the bottom of the building. It's also the fill pressure. It's also the pre-charge on the air side of the bladder of the expansion tank.
all right, so
Okay.
we need to clarify something because I don't want this to hang out there, Rich. When you were asking what the pressure was at the top of the building and the answer was 0, a question came up. Wouldn't it be the fill pressure? So let's kind of answer. I don't know how to answer that the best way, but can you kind of try to?
Yeah, so initially we said there was nothing in this pipe, and I had a device here, a valve, that allowed me to add water to this piping system. And let's say the water ultimately came from the city, and the city water out here in the city street, there's a pipe in the street, and let's say that that pressure in the street was 80 pounds, 80 PSIG. Well, somewhere in my mechanical room, I have to have a fill valve, PSIG. I have to have a fill valve with a pressure regulating valve. So inside there, I have a pressure regulating valve. And initially, all I did was open up this manual valve here to allow my piping system to fill. When I got a couple of drops of water out, I closed this valve, and then I closed the valve at the top. And so I isolated myself from my pressure regulating valve. And so the only pressure I had was the function of the height of the fluid. Then I said I wanted to have not 0 pounds at the top, I wanted 7.5 pounds. So to achieve that, I kept this valve closed, this one over here at the top closed, and I opened up this valve, manual valve down here, and I watched my gauge very carefully until I get 40 PSIG. Now I haven't set the pressure regulating valve yet. I just wanted to fill the system until I got to 40 PSIG. And then I went back and I set the discharge pressure of my pressure regulating valve so it would always give me 40 PSIG as a minimum pressure in the system. So does that help clarify that, Brett?
Yep.
Cool. Any other questions before I erase all these wonderful little
Let me see if I can bring up one of these questions here. Sometimes it's hard. Is that the same? I don't know if how can I ask this here? Is that the same as the pressure at the furthest point? Do you understand that question? I've asked them to clarify that. I'm not sure we can answer that one.
Well, it's the pressure at the top of the building. It has nothing to do with the furthest point. It's simply the pressure at the top of the building. We're not circulating any water yet. So we're not trying to get water to the end. This water is not moving. All I did was set the pressure from the bottom of the building. In a minute, I'm going to show you what happens when we start moving.
Okay, yeah, yeah, you're just talking empty pipes and yeah,
Static,
okay.
we're talking static pressures. Nothing's moving.
Yep.
Okay. That's a great question though, because I can see where the confusion would be. So any other things before I erase this diagram?
Someone asked if it's a 1-story building, and based on what I review, it looks like it's a 5-story building. So
Yeah, I got first floor, second floor, third, fourth, and fifth. So it's a 5-story building, 75 feet tall. Each floor is 15 feet. Good stuff.
yeah. Well,
Okay.
I'll tell you what, we're going to have to save 10, 15 minutes for questions, but we will.
Okay, no problem.
Yeah, no problem.
So now we've established the minimum pressure. So we go back to our diagram. We've established our minimum pressure at the bottom of the building needs to be 40 PSIG. And how do we get that? How did we get that? Excuse me 1 second, Brett. How did we get that? Well, we had the height of the building converted into PSIG. That means the height divided by 2.31 was equal to 32.5 PSIG. We added somewhere between 5 to 10 pounds, and I like to use 7.5. So if we added 7.5 to the top, we get 40 pounds at the bottom. So that's the minimum pressure. So in our simple building, our minimum pressure at the expansion tank is 40 PSIG. That's also the fill pressure controlled by the pressure regulating valve. So here's the pressure regulating valve over here. And this is the water connection to the city main over here. That's also the pre-charge pressure. That means that when I pre-charge this tank, the tank comes from the factory pre-charged on the air side to only 12 pounds. But in order for it to operate properly in the system, before I connect the expansion tank to the system, I have to pre-charge the air to the minimum or fill pressure of the system. We just calculated the minimum pressure. I have to add 40 pounds, increase rather the pressure in the air side of the expansion tank until it gets to 40 pounds. Once it gets to 40 pounds, I can then connect it to the piping system. Any questions about the minimum pressure at the expansion tank, which is also the fill pressure? All three pressures are the same. The fill pressure, the pre-charge pressure, and the minimum pressure are all 40 pounds at the expansion tank.
I mean, there's a question, comment, pre-charge is equal to cold fill, and I think you just covered that quite nicely.
Yes. Okay. So now let's figure out, we have the first one, 40 PSIG. They go a little faster as we go along here. What's the maximum pressure? Well, here's one method. It's not the only one, but here's one method that we can use to establish the maximum pressure. We've got a piece of equipment at the same elevation of all the other piping at the lowest part of the building. And this piece of equipment wants to see a maximum pressure of 150 PSIG. So to ensure that this system never gets above 150, we're going to put a safety relief valve in. We're going to set the safety relief valve at 10% below the maximum pressure in this system. Since the pressure maximum wants to be 150, 10% of that is 15. So 150 minus 15 is going to be 135. Isn't that cool? So the maximum pressure at the relief valve wants to be 135. Well, for those of you that are familiar with the relief valves, they're a very simple device. It's a valve with a disc inside held closed with a spring. The spring is calibrated. Usually there's a knob at the top you can open and close to set the relief valve pressure. But if it gets at the setting of 135, they can leak or drip or weep. Sometimes we use the word weep. Well, we don't want it to weep. So therefore, the pressure that we want in the piping system before we get to the relief valve, let's say I stick a pressure gauge here, we want that to be about 5 pounds below the relief valve setting. So I want that pressure to be about 130 pounds. So I'm going to put that in there next, 130 pounds. There it is, 130 pounds, and that's the pressure also I want at the discharge side of my pump. Well, if the pump has the capability of adding 20 pounds to the system, 20 pounds, then that means that the pressure I want at the suction side of the pump, which in our example is the maximum pressure that I want at the expansion tank, if the pump can add 20, then 130 minus 20 is 110. There's the 20 pounds across the pump. So I want a maximum system operating pressure at the pump suction, which is also at the expansion tank, to be 110 PSIG. Any questions about how I figured out the maximum pressure?
You know what? This question's been hanging out there, and I was waiting to bring it up when you started talking relief valve pressures. Do we need to have a pressure relief valve if expansion tank is sized properly?
Yes.
I know what your answer is to that question, but I wanted to at least ask it.
And the reason is because expansion tanks can fail, bladders can fail for a variety of reasons. And if they fail and the tank fills up with water, if the tank becomes waterlogged, is the term we use, And there's no place for the fluid to expand if it heats up. If we didn't have a safety relief valve, then we'd break something in the system. So yes, we absolutely want safety relief valves.
And not that you can do this at home, but Mike says, good luck finding a 135 PSI relief valve.
You know, that's the second time I've gotten that comment, but yeah, that's a good one. That's why we're showing
That's what he said.
concepts
This
here.
is one method right here.
One method. Okay, so now we've established the minimum pressure, 40 pounds, the maximum at the expansion tank. The rest of the data is really fast. So there's the minimum, there's the maximum. What about our fill temperature? Fill temperature. Well, typically we put the groundwater temperature. And in New England, we typically use 50 degrees Fahrenheit. So your minimum temperature that you're going to get from the ground depends on where you are in the world. If you're in Alaska, for example, those guys typically use 40 degrees Fahrenheit. I've spoken to several people in the Middle East. If we have some people that are in the Middle East tonight, tell me what you have for groundwater temperature. Just type it in, let us know. Brett will tell everybody. I've been told that it could be as high as 80 to 100 degrees. So tell us where you are in the world and what your groundwater temperature. So, but that's the minimum temperature. So for New England, it's 50 degrees Fahrenheit. And the maximum temperature would be whatever we set for our system design. In this case, it's a hot water heating system. You know, if you recall from our original diagram, that's 180 degrees. So now we have the minimum and maximum temperatures. Now we only need two more things. What is the fluid? This is very important. For tonight's discussion, the fluid is water, just plain clear water with nothing in it. And what is the volume of water in the system? The volume of water is approximately 2,000 gallons, 2,000 gallons. Now, in my example, I did a one-line diagram, which I showed you at the very beginning. I put some pipe lengths into the software. I'm using the HSS software. Brett, are you doing the HSS on the next TACO After Dark?
I am in 2 weeks, 2 weeks from tonight.
Yeah, so Brett will show you how you can calculate easily using the HSS software what the volume of the water is in your particular system. But for our system tonight, it came out to 2,000 gallons. Now I have all the information I need to size my expansion tank. So this is really cool. So now I'm going to go live to TACO's website, going live. So I'm going to go to TACO's website. Here is TACO's website. To the home page. Whoa, it worked, first try. And I'm gonna go over here to, just to the right, I'm gonna go over here to selection tools, click on that green bar. And then on the left-hand side, I'm gonna go to expansion tanks, and here is my TACO expansion tank app. Isn't that the coolest thing you ever saw? This is exciting stuff, Brett. I'm so excited. This is good stuff. We are going to use, go ahead.
It's fun. It's great that, I mean, you and I talked about this last week, and we're doing the same. I know I'm doing the same thing, and I can sense it in your voice. We're actually having fun.
Yeah, I'm weird. Let's face it. I'm a bit of a geek. I get all excited about these things, and you know, I just have a good time with all of these wonderful hydronic things. I dream about pipes at night. So let's look at the TACO expansion tank selection app. There it is right there, expansion tanks. The units for tonight's discussion will be in US. You could use this drop-down menu and use SI, which is System International or the metric system, but we're going to use US. We're going to leave the fluid at water, and later on, if we have a few minutes, I'll change that to a different fluid. The piping material, we're going to assume it's copper. We have a choice of either copper or steel for this app. We're going to use copper for our first one. What did we say our system volume was? Didn't we just say that a minute ago, Brett?
2,000 gallons. 2,000 gallons.
We'll put that in there. System volumes. What's the minimum or initial fill or operating temperature? We said that that was groundwater temperature. And for New England, we said that was 50 degrees. We'll put in 50. The maximum temperature is based on our system design, and we said our boiler was going to put out 180 degrees. The minimum or fill operating pressure, we calculated at 40 pounds for our 75-foot tall building. And the maximum pressure that we wanted at the suction side of the pump, we said was 110 pounds. We want a standard tank for this first selection. and I'm going to click on search. This is really cool. Are you excited? Are you ready for this, Brett? Click on search, and the software is going to make several selections for us. Isn't that cool?
Man, that
But
was pretty
before we-
quick too.
I know. Look at how fast that was. And before we go into the selection over here on the right, let me just point out a couple of quick things. Let me get my pen again. If you'll notice, the system calculated the fluid expansion. It said that under these conditions of 2,000 gallons and an initial temperature of 50 degrees Fahrenheit and a final temperature of 180 degrees Fahrenheit, that water will expand approximately 53.44 gallons. Now, it does take credit, gives a little bit credit for copper, and I'll show you how that works in a minute. So in other words, the copper piping in the system also expands as a function of temperature. So the fluid is actually expanding a little bit more than the 53.44 gallons, but the copper pipe is taking up some of that expansion because it's heating up and it's getting physically larger. Now we're going to ignore the plain steel tank for a moment and just focus in on a bladder style tank. In the bladder style tank, the steel container needs to be 95 gallons. And the acceptance volume is the same as the expansion volume. That means that the bladder has to accept 53.44 gallons. So let's go through and look at the first. The software has made this selection of CA 450, which has a physical volume of 119 gallons. Well, that's greater than the 95, so it meets that criteria. The acceptance volume, this is how much water the bladder can hold, 119. And whenever the tank volume is equal to the acceptance volume, we call that a full acceptance tank. That's how you can easily tell from the selection software that you have a full, that looks like an E, sorry about that. Let me scribble that. So we want to say that that's a full acceptance. So I'm going to say FA, full acceptance. And that's because the tank volume is equal to the acceptance volume. So that's the first one. The software has made a recommendation. It says for your expansion tank, you can use a CA 450-125. In this case, 125 refers to the pressure rating. The 450 is liters, and that has approximately 119 gallons. So 450 liters, if anybody wants to do the conversion, is approximately 119 gallons. So that will do the job. The second selection is a CBX. Also, in this case, it's 425 liters instead of 450. So the tank volume is, the steel container is 112. Again, that's greater than the 95. But the acceptance volume is only 61. Well, the acceptance volume of the bladder has to be greater than the expansion. It is in this case. It's 61. The fluid is expanding 53.44. So that will also do the job. Let me put a check mark here. So obviously all of these will do the job. And the third one, if you'll notice, the steel tank is 57 gallons. Well, it has to be a minimum of 95. So if you multiply by the number, the quantity 2 here, if we put that in red to kind of emphasize, that would be 57 times 2, which would be 114. And 114 is greater than 95, so it meets that criteria. Put a little check mark there. And the acceptance volume is 27 gallons. We multiply that by 2, so that comes out to 54 gallons. And the fluid is expanding 53.44, so it meets that criteria for 2. So that expansion tank will also work. And the same thing holds true for the others, but we're not going to talk about the plain steel tank this evening. If we have some time, we'll come back to it. So any questions about how we went from our diagram to the 6 things that we had to decide, and then using our selection app to finally determine what the expansion tank selection should be? I'm excited. I don't know about the rest of you guys, but I am just thrilled. Men and women that are out.
Let's see. What question can I bring up here? You used 180 degrees for your maximum design temperature. And
Correct.
someone asked, this is obviously a hot water temperature, but I do a lot of chilled water designs. Should I use 60 degrees, or what would you recommend for chilled water
For
piping design?
chilled water for New England, I would typically use 110 degrees. So, oh, wow, what are you talking about? The water's not going to get to 110. Well, believe it or not, it can get quite hot. And the reason is that if somebody builds a building, let's say they build a building and put a brand new chiller plant in, a brand new piping system, all of that wonderful stuff, but they don't start the chiller up. Maybe they complete everything, they do all the tests, they make sure it's all pressurized and everything's wonderful. But they do that in April, and the April temperature is nice and cool, and the building's cool, and the water is cool, but it sits idle. And then you get to June 30th, 2021,
Oof,
which just happens to be today.
oof.
And I looked at my thermometer out on my deck this afternoon, and the temperature out there went to 105 degrees. So if you get a heat wave, the water temperature in your building can slowly increase. And it's not unreasonable to think that maybe the water temperature, if the building is not running, the chilled water is not chilling, the chiller's not online yet, the system is filled and all this other kind of stuff, and the water temperature can heat up over several days of just ambient temperature circulating. So I like to have 110 degrees as a maximum so that I can do my calculation.
Excellent. You know, we have a question from Gene, who's in the Montana area, and he says, for a snow melt system, would you use a much lower fill temp?
Well, for snow melting system, again, it's whatever I initially fill the system with. And if my source of water is groundwater, and that's typically between 45 and 50 degrees Fahrenheit for most of North America, I would use that as my lowest temperature. And the reasoning behind that is that, you could pick a lower temperature than that. If you're using glycol, remember, we're in our very simplified system, we're just using water for our discussion. But if you're using glycol, you could have a much lower temperature if you wanted to start it that way. But it's whatever the lowest temperature is you think is going to be in your system, that would be the point at which you would start. Because as the system heats up, you want the temperatures to reflect the greatest amount of expansion. It's okay, by the way, if the expansion tank is slightly larger than what it has to be. It's not going to have any negative effects on the operating characteristics of the system. It's not a good idea to have the expansion tank smaller, because then you have all kinds of problems. The pressure gets too high, the relief valve goes off, and it's not a good day.
We don't like that. We don't like not good days. And then you got into piping, and so the software allows you to use copper or steel. What if I have PEX, and do I have to take a credit for piping expansion? I think you're going to explain that now, right?
I'm going to say that these numbers are relatively conservative. So here's what I'm going to do. I'm going to erase all of these lines here. I'm going to pretend I'm going to erase. Yes, I'm going to erase those lines. There we go. And if you'll notice, I take credit for the copper, and if I change that to steel, look what happens when I click on search. It goes from 53.44 gallons to 55.78 gallons. That's because steel does not expand as much as copper. So if I'm using a plastic material, the plastic material typically expands more than copper. But so to be conservative, I could use either steel or copper. And if I'm using a material that expands more than steel or copper, it actually winds up being a little bit to my favor. So in other words, the fluid would have the same expansion, but the piping might hold a little bit more of that expansion. So to be conservative, I would use steel or copper. To be very conservative, I generally use steel.
Great questions, as usual. The audience is coming through again.
I know, this is fantastic. What else do we got out there, Brett?
Well, when you fill an expansion tank, and I probably should have brought this up earlier, and I apologize that I didn't. When you fill it, how do you know how many gallons are in it? I don't. Maybe we need clarification
No,
on this.
yeah, that's a great question. Let's go back to our system diagram. Let's see, yeah. Yep, let's go back to our system diagram, the very one that we showed at the very beginning of our presentation here. So when the here's the little expansion tank. When the expansion tank ships from the factory, there's no water in the expansion tank on the bladder, inside the bladder. Zero water, 0 gallons. The air side of the tank, and let me go to my cutaway also. Let's go over here. So there's no water in the bladder. On the air side, it's been pre-charged to 12 pounds. That's how we ship them from the factory. We pre-charge the air side to 12 pounds. So when the expansion tank, the bladder style expansion tank that's been pressurized in the air side to 12 pounds, when it gets to the job site, you should be able to use a pressure gauge and put it on the Schrader valve, and you should be able to read 12 pounds. If you don't read, yeah, blah, blah. Can I try that in English words, Brett?
Yeah, you might want to.
If you do not read 12 pounds, that means someone has either let the air out or there's a leak. But the expansion tank ships from the factory. We have no water in it and 12 pounds on the air side. So I think that's half the question. That's half the answer to the question. How much water is in the tank when you first put it in the system? Is that correct?
Yep.
And the answer is 0 gallons. Pretty cool.
Yep.
Any other questions?
Well, in a full acceptance tank, what happens to the air? I think you kind of covered that with your Boyles Law, though.
You mean when the water enters the tank?
Yep.
Yep. So here we have on the right-hand side, we have the bladder. Initially, that bladder is actually collapsed. And the reason it's collapsed is because there's air between the steel container and the bladder. And this void space right here, let's kind of draw a little line. This void space right here, remember this cutaway, obviously this is a cutaway. You can't have any air, compressed air in there. And so the bladder is not going to collapse. But if you ship it from the factory, we put 12 pounds in there. So if you put 12 pounds in there, that causes the bladder to collapse to the smallest possible volume. All of the air inside the bladder is squeezed out. Does that make sense?
Yep.
So ask the question again, because I'm not sure. I think I only answered half the question.
The question was, what happens to the air inside a full expansion tank?
There is nothing on the inside. There's no air, there's no water on the inside of the bladder, assuming that nothing has leaked, because we pressurize them to 12 psig before we ship them from the factory, and that ensures that there's no air or water inside the bladder. And like I said, if you put a tire gauge on the Schrader valve right over here, you can go down to AutoZone or O'Reilly's. You can buy a hand pressure gauge. I think they're like $5. And if you put a pressure gauge on there and it doesn't read 12 pounds when it gets to the job site, then either someone bled the air out by pushing the little stem here on the top of the valve, or there's a leak. But if it's done properly and it's got the 12 pounds, there won't be anything inside that bladder. Isn't that cool?
This is a great question. I'm sure this is from a contractor. The pressure that we need to set the tank for in the field, where do I get that value from?
That's actually, no, that's a great question, because the only place that you can get that is through calculation, and you have to calculate it by using this basic procedure here. You have to take the height of the building and convert that into PSIG. So our example, the building was 75 feet. I divided that by 2.31, assuming by the, yeah, blah, blah. Blah, blah is a word that I say when I can't say regular words. Okay, I'll try that again. The assumption here is that not only is our building 75 feet tall, but the piping system goes from the lowest part of the building to the highest part of the building. So if we want to determine what the pressure is at the bottom of the building, which in our case just happens to be where the expansion tank is located, then you would take that height and divide by 2.31 to convert that into 32.5 pounds per square inch gauge. So that's where you get the initial static pressure without any pressure at the top of the building. Remember at the top, a little diagram, we said there was 0 pounds at the top. So now you have to increase the pressure in the system until, in our case, you get 7.5 at the top, which meant that you had 40 at the bottom. So in our case, we just said for 7.5, add that to 32.5, and that's the minimum pressure at the bottom, which is also equal to the pre-charge pressure. That's the pressure that you're going to add to the air side of the expansion tank and bring that pressure, compressed air pressure, up to 40 psig. And you do that before you connect the expansion tank to the system. And that will also ensure that the bladder is completely collapsed and that there's no water in the bladder.
I want to repeat something that very important item that you just mentioned. Before you connect it to the system. Before you connect it to the system.
Yeah, I mean, some people, they actually will design the piping system in such a way that allows them to open a series of valves so the expansion tank is essentially open, the bladder is open to the atmosphere, which is effectively like having it not connected to the system. But you have to have a series of valves in the right location. We purposely did not show that this evening because everybody has a different method of connecting it to the system for service and for pre-charge and all that other type of thing. But the simplest way to think of it is that you pre-charge the air side before you connect the piping, before you connect the expansion tank to the piping system.
When you were a consulting engineer, did you include that value on your schedules or somewhere
yes.
in your documents?
We always have to include the minimum or fill pressure that we need at the expansion tank. Now remember, in our case for tonight's discussion, the expansion tank is at the bottom of the building. If the expansion tank is at the top of the building, the calculation is slightly different. If we have a little time later after we get through some of these questions, we can show them what the effect is of putting the expansion tank at the top of the building.
And then,
any other questions out there?
Yeah, well, we might be able to answer this one and then you can continue on. What is the best way to test bladder if the bladder has leaks or condition of the bladder?
Yeah, so let's go back to our little cutaway here. This will kind of demonstrate this. Let's go way back. I should have, let me do it the easy way here. Okay, so there is our cutaway on the right side, the photograph. And if for some reason the bladder should fail, water will leak from the bladder to the air side of the system. Eventually, over time, the air that's inside, that's trapped inside the steel container, will go into solution, especially if the system has been running for a while. You know, initially they purge the air out of the system. If you have like an air and dirt separator, like a 4900 from Taco, it's very good at removing air. So as soon as that bladder tears, the water wants to go into, the air wants to go into solution into the water because the water has no air in it. We've taken all the air out with the air and dirt separator. And so it quickly goes into solution, which means that the tank keeps filling up with water and eventually the tank becomes waterlogged. So if you push the little, let me go back here. If I push the little valve on the Schrader valve right here in the top, if I get water out, then that's a pretty good indication that the tank is waterlogged and that the bladder has failed. It's not an absolute, but it's a pretty good indication.
So there's a couple of questions here, Rich, about explain how having more than one expansion tank at two different locations works with a system.
We do not recommend that you have expansion tanks at 2 different locations. You pick one location, and hopefully you've selected the location that is on the suction side of the pump, which is known as the point of no pressure change. So let's go look at another diagram here. Let's go back to our diagram. Here's our diagram. So in this case, if you'll notice, we have a primary pump and we have a secondary pump, and the expansion tank is located, this piping, this connection right here is called a point of no pressure change, and it's very close to the suction side of the pump. And we only want that expansion tank in one location, because if you put 2 expansion tanks at two different locations, expansion tanks will tend to fight each other. So you want, if you put multiple tanks and you want to connect them all to the same location in the piping system. So if I put 3 expansion tanks in there, well, that's a gross looking expansion tank, isn't it? Well,
The
it is
Taco ones
late
do
at
not
night.
look like that. The Taco ones do not look like that.
Yeah, how do we say that? Don't do that.
Don't do that for me.
Don't do that. It's late. Don't do that. This is the time when if you're going to do design work, you better do it in the morning after you have finish your cocktails at night. You got a clear head in the morning, then you can start drawing things. But by now, my drawings are starting to get pretty unreasonable. If you want, you can put noses on your expansion tank. There's a couple of noses. You can have little smiley eyes here, that kind of stuff, happy faces. Yeah.
One of the greatest, one of the most experienced, knowledgeable expansion tank people I know, Bob Barber. He's a long time Taco employee. He's got an ear to know whether a tank is waterlogged or not. So
yeah, we call it waterlogged Bob.
Be careful. I think he's on the call. But
Bob, are you on the call? If you are, type in and tell us you're on the call, because if you're on the call, we want to know if you're really waterlogged or not.
no, he's on. I am. He's texting me. But no, I think if you're if you're in mechanical rooms and you start tapping, and this sounds weird, right? But this is some friendly advice. If you tap on expansion tanks and you can hear the hollowness of it, or the noise sounds different than if you tap on it. When I say tap on it, I'm using my knuckles and I'm hitting my hand, right? That's how I'm tapping on the tank. If it's waterlogged, it sounds different. That's a simple way, That's another way without scaring people by throwing water all over the room.
Hey, you could always design your system to have a scale underneath your expansion tank. That's a good idea.
True. That's true.
Yeah.
All right. What else you want to cover before
Well, I think we've hit the gamut of the stuff that we wanted to cover this evening. I would like to show what happens if you pick a different fluid. We got time for that, Brett?
Oh, yeah. We got time. It's 20 of. We got time.
Do we still have some folks hanging in there?
Oh yeah, there's still over 70.
Whoa!
I know.
You guys are like the punishment.
I think we still have a gentleman that's probably 3 a.m. where he is too, for God's sakes.
So look at this. Was our original little selection here. We put all of the numbers into our selection app. So let's look what happens down here. We said the expansion volume was 55 point. Whoops, let's go back to copper. That's the one I like to work with. I like if they're copper, just for the fun of it. Okay, so copper is 53.44 gallons. Are you okay with that value, Brett?
Yep.
And let's assume for a moment that you pick this first one, a CA 450-125. Again, the 125 is the pressure rating of the vessel. And 450 liters converted into gallons is 119 gallons. Now you install it in the building and everything is up and running. And this is what happens. Either Brett or I or Bob Barber or somebody from Fall River or the rep or whoever's involved, they get a phone call and they'll say, geez, my relief valve keeps going off. What's the problem? And so maybe it gets to Brett or I, and let's assume they call me up and I'll say, well, let's go through the selection process together. And I'll just walk through it step by step. And usually I'll go along the lines, I'll say, okay, I want to confirm that the system has water in it. Water. You have this one we have in front of you on the screen, and it's water. And it's, oh, no, no, oh, no, no, it doesn't have water. It has propylene glycol in it. I said, well, you made the selection based on water, Look what happens if you put propylene glycol in. So we're going to change the fluid from water to propylene glycol. And then let's put in 50%. That's 50% propylene glycol. And then click on search. Look what happens to the expansion volume. It went from 53.44 gallons to 90.27 gallons. Now, in order to keep the pressures that we're interested in, you would have to have a tank volume of 184 gallons, but we don't. Remember, it was originally sized for water, and so the tank is 119 gallons. But if the actual fluid that's in the system, maybe somebody made a mistake and they forgot to put that in the design that they were actually going to use propylene glycol, now the tank is too small. It was only 119 gallons. And so the pressure inside the tank at 119 gallons is going to exceed 110 PSIG. And if that happens, the safety relief valve perhaps could go off and you could have water and glycol all over your mechanical room. This is not a good day. So that's one of the things that we see occasionally. Someone might be independent. Maybe they're off in a different part of the engineer's office and they're doing expansion tank sizing, not realizing that the design engineer on the other side of the office has decided that it's going to be propylene glycol. And, you know, the gentleman, man or woman that's in that part of the office that's doing the calculation thinks it's water. He makes the selection on water, but they actually use propylene glycol. Now the expansion tank is too small. How's that?
That's
And again,
that's
all
not-
we did was change the characteristics of the fluid. We didn't change the volume, the temperatures, the pressures, none of that stuff. But the tank, if it was a 119 gallon tank, too small.
Hey, Rich, I just need to go on record as saying this app that you have in front of you, in front of us right now, looks like one of the easiest apps I've ever seen to use.
I think Bob Barber invented this app. Bob
sure he did.
Barber is the app inventor. He actually did all of the calculations that are in the background for this app. So we should call it the Bob app.
The Bob app.
The Bob app. If you
B-O-B.
say that 3 times fast, can we say that 3 times fast? Bob app, Bob app, Bob app, Bob app.
All right. He wants go to a picture of a CA tank. Bob
He wants to go back to the CA tank.
Yeah, he wants me to, or us, to make sure we mention something very, very important.
Very, very important. Okay, Bob, what does he want us to mention?
All right, it's a little difficult to see, but at the bottom of those tanks on the right-hand side, where that cutout is, if you move your cursor down there, Rich, if you know where that cutout is, there's a valve there. There's a valve.
There's no valve.
Huh?
There's no valve at the bottom.
On the inside.
Nope, there's no valve. There should be a plug.
Right. Do not, yes, I'm sorry, there's not a valve there. There's a plug there. That is only for emergencies. Do not pipe that to drain. It's right in our instruction sheets. It's right. Do not connect that fitting. Do not take that out. It actually voids the warranty. And Bob is, it leads to failures. If you connect a valve to that, over time, that diaphragm or that is going to fail, or it's going to let air in there, and it's going to affect that tank, and it's going to cause failure of that tank or the bladder. So do not pipe that to drain. I can't emphasize that enough.
And you know what happens if you take that plug out and you put a valve in there and pipe it to the drain? As soon as you put the valve in there instead of the plug, Bob Barber's heart begins to flutter. He is automatically connected to every expansion tank that we've ever sold. And if someone immediately takes that plug out, his heart begins to flutter. He doesn't know where the tank is or who took it out. It's just that, you know, it's like through subspace.
Air leaks past the O-ring valve. And
right.
It's
when the air comes out, the bladder fills up with water, and eventually, if it's not a full acceptance bladder, it will rupture. That's not a good day.
All right, so here's the answer to this other question, and you answered it nicely about the checking for water or a bad tank, the best way, this is from Bob now, this is hot off the press. The best way to check a captive air tank is to isolate the tank from the system and open the petcock between the isolation valve and the tank to allow the air to push the system fluid out of the bladder. Once the fluid stops flowing, then check the pre-charge in the tank. If it is correct, highly likely that you have a failed bladder or diaphragm. Does that make sense?
Sounds perfect to me. If Bob said it, it's got to
Yeah.
be true.
Oh yeah, it's got to be true. It's got to be true. So here's a great question. Where the heck did it go? Oh, I hope I didn't. Oh, are you going to cover how does expansion tanks affect the domestic hot water system? Are we going to cover any domestic tonight?
Not domestic. Nope, we're not touching domestic hot water tonight. That's a separate topic. It has its own little idiosyncrasies. This is just for HVAC systems, typically chilled water and hot water.
Yep.
That's what our limitation is this evening.
And to someone wanted clarification, is that plug for draining? Yes, that is only for in an emergency when you have to drain the tank. So keep that in mind. Holy moly. Do
Holy
you fill the
moly.
tank bladder for correct GPM by a flow meter or PSI calculation? Wow, is that
What was the
that makes-
question?
do you fill the tank bladder for correct GPM by a flow meter or PSI calculation? I'm not sure I understand that one.
You never fill the expansion tank with fluid. When you get an expansion tank, before you connect it to the system, there is no fluid inside the bladder. And if it did not leak air, there should be a minimum of 12 pounds on the air side. So there's no fluid in the tank. The only way that fluid gets into the tank is once you properly pre-charge the air side, then you connect it to the system. And if the system is equal to the air charge, the fluid does not enter the tank. The air is 40 pounds in our example. The water minimum pressure is 40 pounds. The water will not enter the bladder. As the water begins to, let's say the air that is dissolved in the water gets removed by the air and dirt separator, now the total volume of water in the system actually begins to contract. And so the bladder remains empty. As the fluid expands, then the water enters the tank. So it has nothing to do with the system flow. If we go back to our system diagram, it has nothing to do with the flow of the water in the system itself. Water enters and leaves the expansion tank at a very, very slow rate. It's a function of the expansion of the fluid.
I just need to clarify that statement, the long statement I read from Bob. So once the fluid stops flowing, then check the pre-charge. If the pre-charge is correct, then the bladder has not failed. If it's not correct, then more than likely it has failed. I apologize for messing that up. So if a tank is missized and they need to add a second tank but are short on space, can they have two different size tanks? Add a smaller one?
You can, yes. Although I generally would prefer to have the tanks the same size. And the reasoning behind that is that if one of the tanks should fail, if the large tank should fail, now you're left with the small tank, and the small tank won't have enough acceptance volume to keep the system within the proper operating pressure parameters. So if I could make a little sketch here, sure. If this one needed to be, say, 150 gallons instead of 100 gallons, I'm just making up a number, I could mechanically put in a smaller tank that's 50 gallons. But what if that larger tank should fail? Now I only have 50 gallons, and I run the risk of not having enough expansion volume. So that's why I would prefer to have, if I'm going to put in a second tank, I want it to be the same size as the original tank.
Here's there's so many different things that are done out in the field that potentially could lead to problems. And here, that's a prime example there, although I'm sure it's been done, but maybe that's not the best way to do it. I have had contractors not change pre-charge pressure. At what point is this critical? Plus or minus 10 PSI, or is there a value?
My answer to that is that the pre-charge pressure needs to be calculated carefully and it needs to be precise. If the minimum pressure at the expansion tank location by calculation, the calculation is done properly, if it needs to be 50 pounds, then that's the pre-charge pressure. I wouldn't make it higher or lower, I would make it at 50 pounds.
So would the partial acceptance tank be used for a well pump to maintain pressure? I'm not sure we can answer that one.
That's not a closed loop pressurized system. That's usually
Open,
for
right?
domestic water. We're not going to touch domestic water or well tanks this evening.
Is pressure fluctuation at the faucets an indication of a failed tank diaphragm? That sounds like domestic, so I don't think we want
That's
to cover
domestic
that.
water. Yeah, we're not going to
Yep.
touch that this evening.
Yep.
This is a closed loop pressurized HVAC system, either it's circulating hot water or chilled water. That's the extent of tonight's discussion.
Yep. What about losing air in the bladder due to permeation through the rubber oxygen/gas barrier? Through the rubber or oxygen.
Essentially, that translates into the bladder has failed. For whatever reason the bladder has failed, when the bladder fails, then eventually the water finds its way into the air side of the tank becomes waterlogged, and that means you have to either replace the bladder or replace the tank. So whatever the reasoning is behind the failure, either the material fails or there's a tear in the tank or some other bizarre thing that happens to the material. From a mechanical perspective, it's the reason for it to fail. When the bladder fails, by the way, in some cases, we'll actually send the bladder back to the bladder manufacturer for them to evaluate the reason for the failure. But from a mechanical perspective, it doesn't really matter why it failed. The fact of the matter is that the water leaks from the bladder side into the void or air side of the expansion tank.
I will also like to at least state these under normal conditions, these bladders should last for many moons. TACO does not make much money, hardly any money on replacement bladders. We're not in the business to sell replacement bladders. Please believe me on that. Yes, I know I work for TACO, but that's not one of our main lines of profit. That's for sure. To say the least, is
I can tell you the life expectancy of a brake line on my wife's car. I can tell you exactly how long it is. It's 17 years. Her car is 17 years old this summer, and the brake line rotted through, and we nearly got into an accident. So, yeah.
And one of our friends, Mike, just said, from a supply house perspective, bladder replacement is a difficult job. And I've seen some installations, instead of replacing a bladder, yes, these bladders are replaceable, and that's part of our sell, and that's something that we do and our competitors do. But I've seen people just replace the whole tank instead of replacing the bladder, just because it is a PIA. Just keep that in mind. And I'm not trying to steer you in any direction. I'm just giving you some facts and some reality to different situations. And I agree with Mike out there. And it probably isn't a small tank either. That's for sure. And by the way, a properly sized expansion tank, and Rich talked about different styles, right? The diaphragm, the partial, the full acceptance. And I'm pushing away the plain steel one for now. Not many, if any, engineers are designing those into systems at all. Anyone sized and bought correctly and installed correctly, will work for a system. There's obviously pluses and minuses in all of them. And to be quite honest, once you get above a certain size, I would go with a full acceptance. That's me talking. The price difference isn't that much. But, you know, it's a little more safety, installation issues, pre-charge, and all of that. Maybe it's oversized a little bit, but nonetheless, if you're in a bind for a replacement or schedule, or you know, you got a hot job, call around. Any one of these can work. Right. Maybe I'm talking maybe smaller projects. Some of our reps have different stockings and whatnot. So please keep that in mind as well. That's something to talk about. What is the market share between partial, full, and plain steel? I think our business model is we're probably 70 to 80% full expansion tanks for commercial. We're talking commercial. Wouldn't you? You probably specified those on almost every project, didn't you, Rich? For all the ones you worked on.
Yeah, I prefer the full acceptance replaceable bladder style tank. That's my personal preference.
Yep. So here's a comment. You were talking about, and hopefully Glenn's still here. I think he is. The pressure on top of a lake is 0. Bottom pressure has to do with depth, height. I don't know what he was referring to. I didn't bring this up earlier, but I guess we can't argue with that, right?
Yeah, has anybody ever seen those submarine disaster movies? Those are great. I love those. I love submarine movies. There's always this, you know, like there's the good guys and the bad guys, and let's assume that the good guys are in the submarine and the bad guys are driving around on the surface with destroyers, and they're dropping depth charges, you know, and always in those movies, the submarine, the captain is saying, he says to the guy that's driving, I don't know what they call a guy that drives a submarine. Maybe somebody was in the Navy and they could help me out. What's the submarine driver job called? But anyway, and the captain runs out and he says, "What's our depth?" And the guy says, "We're at 300 feet, Captain." And the captain says, "Bring us down to 500 feet." And the guy says, "Aye, Captain." And he pushes the steering thing and the submarine goes deeper and he gets down to 500 feet. And then the depth charges are going, you know, and so on and so forth. And then he says, "Okay, bring it down to 1,000 feet." And someone always yells out, "But Captain, it's only good for 800 feet. I don't care. I'm going to go and, you know, get away from those depth charges." So the point is that it doesn't matter where they are in the ocean or where they are in the lake. It only matters what the depth is. And if the depth, the deeper you go, the higher the pressure is. So it doesn't matter if you're in a lake that's, you know, 1/4 of a mile across, or if it's a lake that's 10 miles across. It's only the depth that changes the pressure. Isn't that cool?
I'm not sure we can cover anything else. Now, Bob typed in something here. It says full acceptance units often last 20 plus years. And that gentleman was answered a lot of phones about Fall River equipment over the years. And I'm sure you mentioned that all of our expansion tanks are ASME rated, right? I'm sure you mentioned that at some point.
Actually, I didn't. I'm glad you brought that up. Yes, they are. We are an ASME certified pressure vessel manufacturing facility. So all of our expansion tanks are ASME certified. Very good.
And I'm sure on some of the bigger jobs, projects that you worked on, there may have been times when you needed you know, I'm going to make up a number, a 10,000 gallon expansion tank, and you put in 2 5s or something like that, right? So size could matter, right? Getting it into the room or building or whatnot.
Yeah, absolutely.
Now, if the mechanical room's on the basement, how often did you locate in order to save this tank size up on the roof or up on, you know, up higher?
Yeah, so if you move the expansion tank from the lowest part of the building to the highest part of the building, the expansion tank is physically smaller. That's one of the fundamental principles of Boyles Law. If you go through the calculations, the selection process, you'll find that the expansion tank is physically smaller.
But then you got to locate it up there, you got to mount it up there, and you got piping to get it from up and down. So there's trade-offs, correct?
Yeah,
possibly.
I mean, if you have let's say you have a hot water heating system similar to the one that we have here on the screen, and the boiler room, mechanical room, let's use that word, main mechanical room with the boiler and the pumps and the expansion tank is in the penthouse, then in our building example, the expansion tank will wind up being physically smaller. So the higher you put the expansion tank physically in the building, the smaller the tank needs to be. Very cool stuff.
Good news. We still have attendees, but we do
Well,
not
I'm
have
willing to
any.
stay as long as people have questions. If you
We
have
don't
any
have
other
any
questions out
questions.
there.
We're out of questions. I think I answered most of. I tried to answer most of them. Some privately. I do want to. There was a question about recording of this. You know, that is scary, Rich. We are being recorded. You know that.
I know it. Yeah. Well, that's why I like to tell the submarine story, because, people need to know those stories. Those are good stories.
I tell you, I was so hyped up after last week's class. I couldn't sleep for like an hour. It was unbelievable after class. I maybe the same thing today. I don't know. I just heard a big thunder crack outside, and the big storm might be coming.
Yeah, my wife promised if I worked really hard tonight that she would have some ice cream for me after
Oof.
our presentation.
There you go. So there are no more questions. It's 9:01. I think we covered the gamut on a simple but very important subject, expansion tanks. I will, one last statement from Mr. Bob Barber. Just be careful that when you place the tank on the roof, you still want to connect the tank into the point of no pressure change. The line does not need to be large in diameter. That's Bob's statement. But that's typed at 9 o'clock. Jenny, you are welcome. I'm glad you stayed up. Rich, we still have 56 attendees. My God, these folks, they're probably afraid of what we're going to say next, for God's sakes.
Well, if folks want to ask some more questions, I'll stay on till midnight.
See you in 2 weeks. Thank you. Great presentation. I think we're in good shape. I think we're in good shape.
So,
right.
someone did ask. Someone said you didn't answer my question.
Abe,
Brett, what was Abe's question? We didn't answer Abe's question?
oh, I thought I did. Abe, please ask it again.
Well, can we go back here? Where's Abe's question?
Yeah,
We do not want to leave without answering Abe's question.
I did ask it. Can you find it?
No, he says,
No, because
what was Abe's question?
he was asking about how did you, I asked the question, how do you know what the volume is in the tank when you fill it?
Oh, you mean for the system volume? How do you calculate the amount of water that's in your system?
Abe?
Let's ask Abe. Is that his question? He wants to know how you figure out what the volume of the water is in the system. We got a question from Jim. Does an expansion tank for a chilled water system need to be insulated? If you want to keep the expansion tank from sweating, the answer is yes. You'd want to insulate the tank.
I guess Abe's not going to type in anymore. He's mad at me. So wait.
Oh, wait a minute. Here he is. How many gallons you fill expansion? How do you know? You have to calculate the volume of water that's in the piping system plus the equipment plus the heat generating or the chilled water generating equipment. So in other words, if you had a 5-inch diameter pipe, you can look it up on tables. It says it has so many gallons per linear foot. You have to know the linear footage of all the piping in your system to calculate the gallonage. Now, the good news is that if you use our HSS software, which Brett is going to demonstrate, I think 2 weeks from tonight?
2 weeks.
2 weeks. Then he will show you how the software will calculate the volume of water in the system. And in fact, I use the software, that's what's on the screen right now. And that's how you can figure out what the volume is. For our calculation tonight, we calculated the volume to be approximately 2,000 gallons. That's what we used for our system volume, was 2,000 gallons.
He said let's 200 gallons. So yeah. So in a chilling plant, is the expansion in the evaporator side or condenser side?
It's on the evaporator side, because the evaporator typically is a closed loop pressurized system. On the condenser water side, it could be closed loop pressurized if you were going to a closed cell cooling tower. But if you're going to a more common cooling tower for a condenser water system, the cooling tower would be open to the atmosphere and you would not use an expansion tank, because as the fluid expands, it would simply go up and down inside the basin of the cooling tower. The water level inside the cooling tower would go up and down as a function of expansion. Now, cooling towers evaporate water, and they usually have a makeup valve that's either electronically controlled or usually has a float mechanism. So cooling towers are continuously using up water. So as the fluid in the system begins to expand, the expansion rate is probably going to be less than the evaporation rate. So usually it's not an issue in terms of overflowing, because the water is constantly being evaporated.
I mean, if it's a closed loop system, I don't care if it's evaporator, condenser, but hot water, cold water, if it's closed loop, you would recommend probably putting an expansion tank in.
If it's a closed loop pressurized system, you absolutely need an expansion tank. No question about it.
Right. I mean, Abe, I hope we answered your question. I apologize. So I think we're done, Rich.
I think we're done. So before I turn it back to Brett, I'm going to say thanks so much for everyone to listen in to our presentation this evening. And hopefully you got something out of it. If you think of something over the next few days, you'd like to send an email, be my guest, send it through. Brett and I'd be happy to answer your questions. So with that, good night, everyone. Turn it back to Brett. Thanks again.
Rich, great job as usual. I can't explain how well. Wow, Boyles Law at 8 o'clock at night is fantastic. Oh my God, super. And in 2 weeks from
we shouldn't confuse Boyle's Law with boiling eggs. That's a
Oh.
separate discussion.
I want you to know that I don't want to bring this up now, but I used your recipe today on 18 eggs, and they
come out good.
Hard-boiled eggs by Rich. It's unbelievable.
Yeah, next time we get together, I'll let everyone know my secret formula for making
Remember that
hard-boiled eggs.
When you're doing the introduction in 2 weeks, you got to bring it up. So
sounds good.
All right. Thanks everybody. We'll see you in 2 weeks.
Can I jump in real quick?
Yep, go ahead, John.
I just want to say again, thank you very much for the education. I really thoroughly enjoyed it, and I hope everybody out there got a lot out of it as well. And I really fantastic presentation by both you guys. So thank you so much.
Well,
Thanks, John.
and John, if you want to tune in and find out about how to make hard-boiled eggs, I think we're going to cover that at our next session.
All right, cool. If I can throw in my pasta salad recipe, I think
that's a good idea.
Maybe we can do
Maybe we
that.
should have like John, maybe we could have like not only the technical stuff, but we could have Taco After Dark cooking.
I think that's not a bad idea, because I need hard-boiled eggs for my pasta salad.
There you go.
Ooh.
So hey, hey, this will be all right.
Jim said, I'll remind Rich about the eggs. I would like to know. So you piqued their interest. Thank you,
There's
everybody.
more interest in perfect hard-boiled eggs than there is in perfect expansion tanks.
That's so true. And how about a couple of special guests? Number one, Bob Barber. Thank you for joining, Bob. Your expertise is fantastic. Hopefully some of you know him. Rich and I know him well. John knows him well. He's a fantastic person. Nobody works harder than Bob Barber. And his knowledge is second to none. Just like Rich's.
I used to think I worked hard until I met Bob.
Yeah,
that's very true.
and for you folks that sat in from a commercial side, John Barba is our
no
leader.
relation, by the way. No relation.
Yeah, that's true.
No
they're spelled different.
Yeah. Although I guess we are cousins from other mothers, I guess. I don't know.
but John leads up the whole training team, but his main focus is on the residential side with his coworkers, Dave and Rick. We've talked about it before, and most of you know who he is. John's won numerous awards, as he should. He leads us fantastically. So thank you for staying up all this time, John, and everybody else. And Jim Prisby, I didn't even know Jim was on, another takeover person out there. So that was fantastic. So thanks, everybody. And most people are signing off. Rich, have a good night. Enjoy your ice cream. What's your flavor? Chocolate or vanilla?
Well, I like vanilla, but if I can get strawberry, I will.
Oh.
But I think tonight's vanilla.
Guess who likes strawberry ice cream? Bob Barber. That's his favorite. Oh,
Really?
yeah. I've been out with him a couple of times.
So
He ordered
John
strawberry
and
ice
Bob
cream.
aren't brothers. Bob and I are brothers. We're strawberry ice cream brothers.
For me, anything with peanut butter in it goes right to the top of the list. That's all I'm
There
saying.
you go. There you go.
And my
All right.
birthday's
I'll
coming up.
send you
Guys.
some
My
Reese's.
birthday's coming up, guys. Just a hint.
Nice,
All
nice.
Thanks, everybody. Appreciate
All right.
your time. We'll see you in 2 weeks. Enjoy
All
the
righty.
4th.
Take care,
Bye,
everyone.
John. Bye, guys.
Good night.